All right, guys, this is it. We've made it to the big times. We are now going to look at, prove, verify all of the things for the fundamental theorem of calculus. It took all these months of getting all those basic skills, the idea of derivative, the idea of limits, all of that solidified to be able to reach the point where we understand the fundamental theorem of calculus. This is the theorem that relates the two things that are seemingly totally unrelated, and we find out that they're connected, and that is the idea of area under a curve and a derivative. Okay, so first of all, let's begin by saying that f is a continuous function on an interval from a to b. And also, you might notice that a lot of these theorems and definitions and things all rely on f being continuous, which is why we spent so much time talking about what continuous means back in chapter 2. But basically, we're looking for a graph that is connected everywhere. No holes, jumps, or asymptotes on an interval. So it has to be continuous on an interval. And let's say that it looks kind of like this. And let's, for the sake of this theorem, and you'll understand why later, we'll go ahead and call this the t-axis. So in place of x, we'll have t. And then the y-axis will be f of t. And so we'll have our nice curve. And we're looking at the area under that curve on the interval from a to b. And let's go ahead and now define another function, which will be capital letter F of x. And we're going to define that function as the area between a, which is the lower limit, and x, which is going to be allowed to vary, of f of t, which was this curve right here, dt. And you can see the reason why I chose to use t. It's really kind of more like a dummy variable. It's just our independent variable. But I didn't want to confuse it with this x. Now this x is going to be allowed to vary. So I could either place the x here if I choose, or I could place it over there. I can place it wherever I want. But the function, capital F of x, would be, wherever I do choose to place that x, it would be the area between a and x under the curve. And you can see that wherever I choose to place the x, it's going to change the value of that area. If I place the x very close to a, my area will be tiny, be small. If I place the x further away, closer to b, I would have a much more significant amount of area. So this function varies or depends on x. As I move the x from left to right, that will increase or decrease my area. So this function of area depends on x. And it's the area between a and x under the curve of little f. Okay, so that's our function. What we want to find out, what we want to do is find out what does the derivative of capital F of x equal. That's what we want to find out, because the theory is that it equals little f. The theory is that the derivative of capital F equals lowercase f. And so we want to find out if that is in fact the case. And so similar to what Professor Berger did in the video that we watched last week, is he said, okay, let's say that this was our x right here. Let's just go ahead and call that x. And so right in there is my f of x value. It's all that area between the curve f of t and the x-axis between a and x. And let's say that I choose a little offset. I pick a point that's just slightly moved to the right from x. And so there's this sort of change in x going on between x and this new point. And so we could say this new point is x plus the change in x. And then back in the days, back in chapter 3, this is what we called x plus h, and we called the delta x h. It's kind of a similar idea. So what we want to notice now is that if I slide that x over, now I have x plus delta h, I would now have this additional area added on to my original area. So if I slided that point over to right here, I now have some additional area. And if I look at what that additional area would be, it basically would be the area from a all the way to x plus delta x. So that would just be f of x plus delta x. That's all the area from a to x plus delta x. And then subtract away f of x. Because f of x was the area between a and x. F of x plus delta x is the area from a all the way to x plus delta x. So if I take all that area and subtract off the red area, I have an equation for the blue area. And you could say that we find area by doing base times height. So I'm going to figure out what this equals in terms of f of x. Well, since delta x is such a teeny, teeny, teeny offset from x, this height right here, which would be f of x plus delta x, is not much different from this height right here. And so I could say, okay, the base is equal to delta x for this blue area, and the height, I could say, is approximately the same thing as this height right here. This height right there was f of x. This is the value of f when you plug x into the curve. This height right here is f of x plus delta x. And since we're saying that this is such a teeny offset away, it wouldn't be that far away. It'd be really close to f of x. So we could approximate it pretty closely by just using this height of f at x. And so my base would be delta x of this blue area, and my height could be approximated by f of x. And that would give me a close approximation of that blue area, which we said here was equal to all of the area from a to x plus delta x minus the area from a to x. Okay, now we have this established. Let's go ahead and use the formal definition of derivative to find f prime of x. According to formal definition of derivative, f prime of x would be equal to the limit as the change in x approaches 0 of capital F of x plus delta x minus capital F of x all over delta x. And if you wanted to replace all the delta x's with h's, you could do that, and you could see that it's pretty much just the formal definition of derivative. So maybe I'll just go ahead and do that now. So we could think of delta x as h here, we could think of delta x as h there, because h was just a change in x. So you see here we basically have formal definition of a derivative. Well, we looked at earlier that this part right here, the f of x plus h minus f of x, is approximately equal to base times height. Delta x times f of x. Oops, and I don't want to forget the limit. So we have limit as h approaches 0 of all of that divided by h. Oh, and I can go ahead and call this h as well because that's just delta x. So wherever there's a delta x, I can just call that an h because they basically mean the same thing. Okay, and then I see that these h's cancel out. And so then I have the limit as h approaches 0 of f of x. And since there's no h's in there, you could think of f of x as like the constant, and that limit just equals f of x. So we basically have proven that the derivative of capital F, which remember was the area under little f up until x, that derivative is equal to this curve f of x, little f. So we basically have proven that f prime of x is equal to little f of x. And that right there is the fundamental theorem of calculus. It's one of those things that just kind of, it's very fascinating. Who would have thought that if you found the area, something that seems so unrelated to calculus, it's geometric, that if you found the area under a curve, that area would act as the same function as the antiderivative of that curve. It's fascinating, and it has so many applications, which is, we'll get into some of them in this section, and then from here on out, like chapters 6 and 7, it's all applying this fact that I can use the area under a curve to find an antiderivative, or I can use antiderivative to find area under a curve. Okay, but let's look at part 2 of this fundamental theorem. So this part is a little bit more abstract. It's a lot more analytical. We're thinking of area as a function of x. We're thinking of this integral expression as a function of x. It requires a lot of concentration, a lot of thought. Part 2 is a little simpler. It's how we evaluate integrals. So basically what part 2 says is, same sort of conditions as part 1. Okay, we have f is continuous on an interval from a to b. And we have already noticed that we have this function f of x that's equal to the area from a to x under f. So we've got that, and we proved in part 1 that the derivative of this function is equal to that function. So knowing all of this and having all of this sort of as the condition, we could basically say then that this implies that if you want to find the area under a curve between A and B, because it's continuous for that whole time, you simply need to find the antiderivative, evaluate that at B, find the antiderivative, evaluate that at A, and that would be the area under the curve between A and B. Another way of writing this is you find the antiderivative and you evaluate that from A to B. That's kind of what this little side bracket means. Like we're going to evaluate that from B to A. So these kind of mean the same thing, and I'm going to use this notation a lot because you'll see that a lot in different texts, and I want you to get really, comfortable with it. Okay, so we're going to go ahead and use part 2 right now. It's the easier one to use to solve example 1, and then we'll kind of back up and use the part 1. Okay, so in example 1, we're being asked to evaluate this definite integral using part 2 of the fundamental theorem, which means we're not going to use area formulas, we're going to use antiderivatives. So I basically need to find the antiderivative of 3 to the x. So I need to figure out what function would f have to equal. What would big F have to equal for its derivative to equal 3 to the x? So we need to think about that, and I need you to think back to your exponential functions. In fact, maybe I'll go ahead off to the corner, sort of like a little mind bubble. Remember that when we took the derivative of an exponential function, it basically equaled itself and then times ln of a. So I'm thinking that f of x has to have a 3 to the x in there somewhere, because that's the only way I'd end up with a 3 to the x in the derivative. So let's say it was equal to this. If I found f prime of x, I'd get 3 to the x ln 3, which is not what I have here, but I'm close. So how would we be able to get rid of that, so to speak? Well, I'm thinking if we have it be in the denominator of our original function, that means it would have to be in the denominator of our derivative, because this would just be a constant. This would be like 1 divided by ln 3. That's just a number. It's just a constant. And the constant multiple rules of derivatives say you have to multiply that same constant to the derivative. So I'd have 3 to the x ln 3 divided by ln 3, and that would cancel that out, and I would have 3 to the x. So I have successfully found my antiderivative. My antiderivative is this right here. But now I need to evaluate that between -1 and 2. And as usual, I'm running out of space. So I'm going to have to work with this little space over here. So I'm going to take that antiderivative and evaluate that from -1 to 2. Meaning I plug 2 in for x. So I have 3 squared over ln 3 minus, and then I plug -1 in for x. And then I would end up getting 9 over ln of 3 minus, and then this 3 to the -1, that actually becomes 1/3. So it becomes 1 over 3 ln 3. And then, if you bear with me, I can maybe flip this over to the back. So this is what we had. We had, it was 9 over ln 3 minus 1/3 ln 3. So now I need a common denominator, so I can multiply by 3 over 3 to the left fraction. And then I would have 27 over 3 ln 3 minus 1 over 3 ln 3. And that would be 26 over 3 ln 3. And that would be what you call an answer in, quote, exact form, because it doesn't have any decimals. Because I could plug ln 3 into the calculator and get like a decimal version, which is considered approximate form, but this here is considered exact form. And that would be considered the area under that curve of 3 to the x from -1 to 2. Or you could also consider it as, I guess, the antiderivative evaluated at those points, -1 and 2. And so for the next video, we'll go ahead and proceed on to page 2.